Hello and welcome to AQA GCSE Physics 9-1, Chapter 1 Conservation and Dissipation of Energy, Chapter 1.1 Changes in Energy Stores. So let's get started. Alright, so the first thing that we'll be looking at in this energy chapter is a very important idea. It's called the conservation of energy. You may have already heard about it. And what it says is that energy can never be created or destroyed, okay? So all the energy that's available, okay, in the universe, okay, is just there in the same amount. It can never be created or destroyed. It can only be transferred between different energy stores. And what do we mean by energy stores? Okay, so an energy store is just basically a different way of storing energy. Okay, so energy stores are all different ways of storing energy. Okay, and when you provide energy to an object, you are essentially transferring energy to one of its stores. Okay, it has different types of stores, and this might not make sense in the beginning, but once we look at some examples later in this video, it'll all make sense. Okay, so once again, yes, just transferring energy from one place to another. So now let's look at the first example of a type of an energy store called a chemical energy store. Okay, and what does this refer to? So if we make a link to chemistry, you may have watched the first video on this channel, which is a chemistry video. If you want, you may just want to look at it, but you can make sense of it without watching that video. So if we make a link to chemistry, this includes the energy in the bonds between atoms. Okay, that's the energy stored in the bonds between atoms. So that's a type of energy store. So for example, in an exothermic chemical reaction, basically what this means is that an exothermic chemical reaction is where energy is transferred to the surroundings in the reaction. Okay, so in this reaction, some energy is transferred from the chemical energy stores of the reactants to the thermal energy stores of the surroundings, making them warmer. And we'll look at this thermal energy store, we'll look at this idea in the next slide, but for now, yes, the bonds between atoms, remember that, of course, and the chemical energy stores of reactants to the thermal energy stores of your surroundings. Okay, which is why in reactions like combustion reactions, which is why I've given this picture here, when you're burning a fuel, okay, in the presence of oxygen, right, a fuel reacts with oxygen, that's called combustion, and you would release energy to the surroundings, right? You would release energy to the surroundings in all these examples. Energy would be released to the surroundings. So now we were thinking about thermal energy stores, which we saw. I think the word thermal itself would give you an idea of what we mean, even from the previous slide, chemical energy store to the thermal energy stores, which would make it warmer. So it has something to do with temperature and everything, right? However, there is a huge misconception. Many people, while coming into this topic, they think that two objects having the same temperature means they have the same level of thermal energy. That is incorrect. That is incorrect. You must understand that two objects having the same temperature does not mean that they have the same level of thermal energy. And to kind of make sense of it, let's look at two water bottles at 50 degrees Celsius. Okay, both of them are full of water. We have a smaller one and a bigger one. So even though they have the same temperature of 50 degrees Celsius, they both do not have the same level of thermal energy, because what we essentially mean by this word temperature, we just take it for granted and just use it in our everyday lives. But temperature, what it means is you can think of it as a measure of average energy per particle. Okay, average energy per particle. Okay, that's not exactly what it means, but you can think of it like that. It's somewhat like that, to make you understand why thermal energy and temperature are not interchangeable. Okay, so if this is average energy per particle, okay, and both of these bottles have this same temperature, clearly this has less water, right? Less water, and therefore less water particles, and this one has more water particles. because it's a bigger bottle full of water. Okay, that means if our average energy per particle is the same for both bottles, and we have more particles here, that means we have more thermal energy, right? More thermal energy. If you just pause the video and think about it for a while, if you can't understand, it's a simple idea, but if you can't understand it, just pause the video and visualize for yourself. We have more particles here with the same amount of energy. We have less particles here with the same amount of energy. So this one has more thermal energy overall. Therefore, temperature and thermal energy are not interchangeable. Please keep that in mind. Okay, and there are other energy stores like let's just rub that out, but there are other energy stores like the gravitational potential energy store, elastic potential, magnetic, electrostatic, nuclear energy stores. There are many. We'll be looking at that in future videos. And generally in different scenarios, you'll literally get the hang of it. There's no requirement for you to know exact definitions, it just comes, and you'll be able to see that while doing practice questions. We'll do videos on practice questions. You'll be practicing practice questions and you'll get the hang of it eventually. So now another key idea is that energy can be transferred between energy stores in three different ways. One, either mechanically, which is where a force does work on an object, and we'll come back to the idea of work in another video. Sorry, I know I'm saying all these different things. We'll come back to it in a different video. This is just a starter. If you don't understand it, it's completely fine. Okay, so a force doing work on an object, that is mechanically transferring energy. Electrically, work done or force done by moving charge, right? Work done on a moving charge. Okay, work done by a moving charge, energy is transferred by this moving charge. And then either we have waves as well. An example of this is electromagnetic radiation, like X-rays, gamma rays, visible light. Again, we'll come back to it. Or heating. We have different types of heating, like conduction, convection, which we'll also look at. But heating in simple terms is literally self-explanatory, I think. So let's take an example of a light bulb. So let's say we have a battery here, and let's draw out a wire. Okay, let's zoom in on this wire. Of course, we have circuit diagrams which we'll look on in the electricity topic, I think. These are not accurate circuit diagrams. We do have something like that we'll look on. So let's say we have this light bulb, and let's say we have moving charges. Okay, we have moving charges. Again, we'll look at what they exactly mean by moving charges in the electricity topic. But for right now, you can just think of them as these small particles, okay, moving charges, and we have them passing through one by one, right, in series, and they pass through the bulb as well, okay, and then we go. So these moving charges are transferring energy, okay, from the chemical energy store of the battery, right? Chemical energy store. Let's just write that out in full, just to make it understandable. So we have the chemical energy store of the battery to eventually, we're just looking at, there might be intermediate energy transfers, like to electrostatic energy, electrical energy. You might see it named in many different ways, but right now, simplistic manner of thinking, we're just looking at the starting energy store to the ending energy store where energy is being transferred. So it starts off as in the chemical energy store, right? And energy is being transferred by these moving charges to light energy, right? There might also be some heating and the thermal energy of the light bulb filament, but at the end, what we actually want from this is light energy, right? Light energy, which is also going to be transferred in the form of waves, to the surroundings as well. So this is light energy, okay? And now let's look at a system is an object or a group of objects that we observe or include in a particular interaction, okay? And in an open system, energy can be transferred into and out of the system, okay? However, in a closed system, energy can only be transferred between different stores or objects within the system itself. So a good way to sum this up is that in a closed system, both matter and energy, objects and energy cannot leave the system or enter. We just look at that system. We don't care what's happening outside, and what is happening outside cannot affect what is happening inside. It should not affect what is happening inside. However, in an open system, energy can be transferred into and out of the system. Okay, and this will make sense again with an example. So let's take a kettle. Okay, let's take an electrical kettle, just connected by wire, and let's fill it up with water. So we can look at this as an open system or a closed system. It's entirely up to you how you look at it. Okay, so in an open system, if we take this as an open system, then let's just have one object, okay, which is just the water. The liquid water that we have here is the open system. Okay, let's only include the water in our open system. Remember, it can be a group of objects or just a single object. So if we just take a single object in our system, in our open system, we have the water. Okay, and here, once we have heating, right, energy is transferred to the water by heating. Energy is transferred from the heating element of the kettle because it's powered by electricity, right? Heating transfers energy to the water. And since we're just taking the water in our open system, nothing else in the system, we don't care about the heating element, we're not considering it in our system, that means energy is being transferred into the system. Okay, energy is being transferred into the system, into the open system. Because remember, in an open system, energy can enter and leave. However, if we want to take it as a closed system, the only way we can get the full picture of where the energy is coming from is if we take our objects in the closed system as the heating element and the water. Okay, so that means now we can say that no energy at all leaves this system. No energy leaves this system, which consists of the water and the heating element. So that means within this, okay, we have the heating element transferring energy to the water. There's no net energy change in this closed system. Therefore, matter does not leave, obviously. We still have the water and the heating element. They do not leave the system. And energy does not leave the system at all. Okay, it's being transferred within the different objects, within the objects, right? It's being transferred from the heating element to the thermal energy store of the water. But we're not actually changing the amount of energy that is inside the system. So I've given as in-depth as I can in terms of this explanation. You can definitely do some extra reading using the textbook provided by AQA from your teachers, and this will make a lot more sense. I highly recommend doing practice questions, summary questions that are found in the textbook, past paper questions definitely at a later stage, and this will all make sense. It will become secondary nature to you. So that's it for the first video.